Okay, I think we'll go ahead and get started, and I just talked to Sue. We're going to do introductions for the council meeting after today's seminar. So good morning and welcome to today's research seminar, which is being offered by the Center for Transportation Studies here at the University of Minnesota. My name is Linda Prisen, and I'm Director of Research Administration at CTS. And this seminar is being held in conjunction with a meeting of the CTS Safety and Traffic Flow Council. And as you'll notice, we are having a webinar that is being streamed live on our website in addition to the audience here in our room today. So just a couple of items before we get started. We will have a live audience, and a recorded copy of the seminar will also be available after the fact, so probably about a day's time. If you know of somebody who missed today's seminar who might be interested, we'll have it posted on our website in about a day. Please hold your questions till the end of the seminar. You'll notice that this microphone isn't projecting in the room, but it is projecting to anyone who is listening online. So when we have the Q&A at the end of the seminar, we'll ask you to use this microphone so that those who are listening online or being recorded can hear your question. And then for those of you who are viewing online, there is a mechanism to type in a question on the upper right-hand corner of your screen. So at the end of the session, we'll also monitor that and see if there are any questions from our online viewers. All right, so at this point in time, I'm going to introduce today's seminar presenter. And Chen-Fu Liao is a research engineer at the Minnesota Traffic Observatory here on campus. Chen-Fu's recent research includes auto-calibration algorithms for way and motion sensors, and he's also working on a decision support system to assist visually impaired pedestrians at intersections, and that's the project that you'll be hearing about today. In addition to his research, Chen-Fu also develops simulation modules for education for courses and K-12 audiences. So at this time, I'll turn it over to Chen-Fu.
All right, thank you, Linda, and good morning, everybody. And I hope that everybody can hear me fine, including the online. But I'm thankful for the opportunity this morning to present this project to you. And this project is dearly to me that I have the opportunity to volunteer my time to better understand the visually impaired people once per week with clients from the Vision Loss Resource Center in Minneapolis. So the title today is about signalized intersection crossing for the visually impaired. And before I get started, I would like to acknowledge the people and organizations involved in this project. And this project is funded by the readout through the UTC University Transportation Center program, Vision Loss Resources, and MnDOT, Steve Miskin and team that provide access to the signal controllers. And we have O&M specialists that helping us, Linda Spalding, and students and professors at the university here, helping us to understand the human factor and human behavior, how we could better provide information for people that are visually impaired. A quick outline on this today's presentation. First, I will talk about the background about navigation and wayfinding in general for visually impaired. Accessible pedestrian signals. As you see, there's more and more APS signals at the intersection. The motivation of our project, our approach, and some survey results from our previous study on trying to understand if we want to provide information to them, what kind of information is useful and through what kind of type of media. And I'll talk about the prototype system, and hopefully I'll be able to do a brief demo on the user's interface part. I checked the server signal in this room here. It's kind of two-bar here. If I'm closer to the window, I think I got better signal here. So I'll try that for the demo. And then I'll talk about the field experiment, which is ongoing right now. Then we'll talk more detail about that with some concluding remarks afterwards. So a quick low vision statistics. According to a report from the Alliance for Aging Research in 2010, that every 7 minutes in the United States, they are people, get blind or visually impaired. And in the United States, there's 3.4 million people, which is about 3% for people 40 or older that are legally blind or visually impaired. So the forecast from this report saying that by 2030, the visually impaired person in our country will be doubled. I think that's it's kind of scary, and as we all get older and the vision, becoming issues. there have been some systems in Europe, and the next couple of slides I will talk about briefly about a couple wayfinding and navigation system in Europe particularly. And in Europe, first one is called the e-Adapt, and this one is demonstrated in 2010 in Stockholm at the ITS World Congress, that they're demonstrating using the smartphone device with additional inertia measurement unit, that they'll be able to track the location of a person, and through the cellular and Wi-Fi communication, and together with the accurate digital map, that they'll be able to map the bench, light post, and entrance of a subway station very accurately, and by providing that kind of navigation information to assist the visually impaired to get to their destination. And the next one here is called NOPA, and this one is primarily focused on providing information for persons that are visually impaired to take the public transit to their destination. Next to the one on the top here is called ASKIT. It's kind of a Europe funded by the whole Europe Union, that focus on providing the information in general, what kind of information infrastructure could be developed to share the information basically for everybody, and not just particularly for visually impaired. And these being testing at 8 cities in Europe currently. And the last one here is called Mobile in France, and they again focus on the real-time information and primarily on the transit. I mean, when the person that's visually impaired get in on the bus, where do they go? Where do they get off? And for example, people with dementia or Alzheimer, that if they get lost, and someone might be able to find where they are by using a device on the phone or some other device to know where they are, where do they go, things like that. In the United States, commercially available, there have been a lot of devices, that GPS devices that are available for helping the visually impaired getting around. And for example, the Cellular GPS for the Braille note, and combined together with the Braille note device, and it will speak to the users about the location, things like that. And all the other devices like Tracker Breeze, again, a talking GPS, Street Talk, Mobile Geo. These are similar type of device that providing when a person is at a location and rely on the GPS information and some mapping information to tell them where they are and how far away from the nearby landmark or building, things like that. And as you may know, that the GPS accuracy is an issue that I have the opportunity to witness some of those systems that are running in live and demonstrating, and sometimes tells you that, okay, that building is 2 blocks away, you are 2 blocks away from that, but it's not necessarily accurate. And so GPS accuracy, it's an issue, but these are the technology used primarily using the GPS and mapping information to identify the locations of the users. And recently, as more popular, people are using more smartphone and mobile device, and there's lots of applications, apps that are available on the smartphone, iPhones. And here just listed a couple examples. I mean, for the Android phones, that they are, walkie-talkie, basically tells you where you are, and with respect to the map, and tells you a turn-by-turn walking direction. And this the intersection called Intersection Explorer. So you can use that apps on the phone and use this application to explore, but just like you kind of browse through the map and telling, okay, where is this and where do you go, by using the application on the phone. I think the iPhone is, again, a GPS application. I mean, there are 2 in here, and Cellular, the kind of application used called the Cellular Look Around. And basically, it's a similar application we had before. Instead of having the visually impaired purchase another device, basically now they develop apps that allow them to use that apps on the existing phone. And again, it will basically talk to you about the street and location where you are and what are the nearby buildings or landmarks. And as I show in the bottom right, that's the graph here shows they are smartphone with Braille. I mean, basically a Braille smartphone that it could be available. Some challenges at the intersection. As you know, that without vision, I mean, crossing an intersection, it's difficult and tough. So, I mean, from our understanding, from our survey, I mean, among the visually impaired persons, that not knowing the geometry at the intersection, okay, and then they need to know where's the edge of the street. Locate a crosswalk if there's a crosswalk. Okay, interpret the signal and traffic pattern. What is the timing pattern, so they can determine when to cross, and align toward the crosswalks as they cross, that they will stay on the crosswalk. Locate push button if there is one, and oftentimes there's no push button at all. And determine when to cross and maintain a line to when they are crossing. So these are some challenges that the visually impaired person face at the intersection crossing. Some literature's reports from in 2005, Barlows and her groups that reported that there's about 50% of the visually impaired crossing during their study. They started during the cross interval. Okay, and about 27% of all the crossing without existence ended after the onset of the perpendicular traffic. So which means, well, it basically says they don't know exactly when is the time to cross. Okay, they basically based on their hearing and to determine when is the pattern. If they don't hear anything, that means maybe it's safe to cross. But what happened is because they kind of starting late and maybe veering a little bit, and 27% of them, they do not have sufficient time to finish their cross, which means, I mean, they're still at the crosswalk, but the signal is already turned green on the perpendicular direction. 72% of those participants that they started with a pretty good alignment. They can use their hearing to hear the traffic patterns and kind of have a pretty good alignment, but 42% ended outside the crosswalk. Okay, so this is a veering issues that. And David Guth and his group in West Michigan basically were training the visually impaired, to use the new cue to enhance their judgment with technology, may be a more effective way, because you can teach so many kind of different strategy to help them to go through intersection, but maybe the technology can help them to better understand what is going on in the environment and provide a more effective decision support system to guide them through the intersection crossing. Some of you may be familiar with the APS, kind of brief APS history. The first APS in the United States started in 1920s, but it's not included in the MUTCD until 2000. And look at that gap, 80 years. And obviously, the visually impaired group is probably not, speaking out, or is not considered by the general public, but recently there's been a lot of awareness about the need for visually impaired to make the street more accessible, more livable for them. And the older system that they use, the two-sound system, cuckoo and a chipping sound. And I was told that there's still one system here in Minnesota, but I haven't seen that. But basically, when I was in Arizona, basically there are two sounds. One direction, north-south, they provide you the cuckoo sound, and east-west, they provide a different sound. The problem with this is, well, the users need to remember, okay, what does this sound mean? Is that east, south, or north? East, west, or north, south? If they get confused, then they lost. Then they lost where they are. And that basically adds additional layer for the visually impaired to understand what does this signal means. And sometimes those signals they only turn on when it's a walk signal. And there's no sounds at all in the regular operation. So you don't know if there's a APS there or not, and you only hear it when it's walks. The walk sign is on. And in the mid-90s that it was integrated with a push button, and I think I kind of explained about this. We'll skip to the next. In 2005, there's a federal lawsuit about accessibility for visually impaired at the signalized intersection. So basically, I won't read through this, but basically, the law required, everybody got the same opportunity to, at the intersections. So the federal finds that the lack of accessibility for blind pedestrians is a violation of the ADA. So this is the lawsuit, and after this, as you see that the federal government has been a lot of focus on for all the new intersections. I think I don't know if it's a mandate or requirement now, but all the new intersections require APS at the intersection, and all the existing one that if you are renovating that you will require APS, and for the existing intersection that the public agency will require plan to include the APS in their future plans. So some of those the latest generations of the APS system, as you see that on the top picture, it shows that there's even the map, a tactile map attached to that push button. But these are available that in Europe and Australia, but not in the United States. And the bottom one, I believe, is the one that used in Minnesota here. And basically, the push button that is constantly emitting a 1 Hz tone, beeping tones to guide a visually impaired person that where the push button is. And also on the push button, there's a tactile arrow telling that the crossing direction. Okay, and then some of the system it has automatic volume adjustment, because during rush hours the traffic gets so busy it's hard to hear this system and hear the information. And as you see that there's been lots of APS installed. There's one on campus here at Lindale Franklin, and several, Snelling and Mindat has been installing a lot of APS recently. And here's some concern about APS. Obviously, cost is an issue, so you need to add additional costs. Noises, even from the visually impaired community, they do not like that noise sometimes. And nearby vicinities, business or residential, they don't like that constant beeping noises. And for installation, location of a push button, it's a concern. There's no standardized location of a push button. And when we ask about, okay, the visually impaired, when you cross, do you find the push button and press that push button at all? Over 50% of them, they don't even care, because they don't know if there's a push button there or not. If there is, then they need to find it. And when they find it, that means they need to come back again and find their crosswalk, because the push button is not right next to the crosswalk. So oftentimes, costs more work to them, and they, don't want to bother finding the push button or even push the button. And here, a quick list. This is not the exhaustive list, but these are some factors that usually public agencies use to consider. Obviously, it will be good to every intersection with APS, and with efforts, resource availability. These are kind of the priority they use to determine where should they put those APS first. Location to a nearby, a facility that there's lots of a visually impaired person with activities, and how close are to alternate crossings and transit stops and key facilities, things like that. Intersection is another key factor. How complicated is this intersection, and how wide is this intersection? Pedestrian accident records. What if if that pose the potential threat of danger, things like that, and if there's a demonstrated need and push button existence, things like that. And these are basically kind of a priority. And this is very helpful for us and also for visually impaired. A couple of weeks ago, I had a chance to present this to the visually impaired community. And oftentimes, there have been people asking for, installing APS here and there, but they do not get it, and this is helpful to help them understand about the priority from the public agency's perspective, because they cannot right away to accommodate all the needs, but it's in there on the list. So there are some controversy, as you know, that in the blind community there are two big groups. One is kind of support education, rehabilitation, and to support people to get education and to learn the skill they need to get on the street, to be more independent traveler. And there's another group is, well, they want people to be more independent, but they don't think education is needed. They think, well, people, they should be able to learn it by themselves, learn it independently, and without vision, they should be able to be an independent traveler without additional information that is designed particularly just for them. And they see that as kind of humiliation or whatever. Basically, well, you just designed this for us, and you're kind of looking at us as kind of, well, maybe different from the regular person. So these two different groups, well, one group is, oh, yeah, that's great, that information, more information is great, but the other group, well, this is kind of discouraging, and they don't want people to use that. And right now, the other group, disagree with the APS. I think they kind of lower their tone a little bit. But again, there are two different groups that one wants it and the other group don't like it. So our motivation is, well, maybe we can do something, more at the more personal level, like a cell phone. If you like it, you use it, and if you don't like it, you don't use it. And everybody, there's always a people using cell phones. Somebody don't use the cell phone. Doesn't matter. So it's more of a personal choice instead of at the infrastructure we installed for you, and some people like it, some people don't like it. So it's a kind of a more personal approach. And these that will be able to provide more of a geometry information. Okay. So when they're at the intersection, they can know what are the streets and what kind of general configuration of that intersection. And also they need to find a push button. Maybe with a more personal approach that they don't need to find a push button. And maybe they can activate, if they are registered visually impaired person, legally blind, that they can activate it from their smartphone, things like that. And the message that we can speak to them through a voice message and tell them, what are the traffic conditions and intersection signal timing information, things like that. So what we did is in our phase 1 study, we did basically surveyed a group of visually impaired person. And basically, we're telling them, if we are going to provide you a mobile device that help you at intersection crossing, what type of information will be useful, and through what kind of media would be useful would you like to have those type of information? So they would like to have additional information about the intersection, because they do not know the information about the intersection. Short auditory phrases, and you'll be able to repeat it. Because oftentimes, if you talk a long sentence, they don't know what's that about, and they don't catch the keywords. And they should not interfere with their existing capability to listen and to cross using the white can, and use tactile cue for dangerous warning. Because in some of those questions, we ask him, okay, when we provide a feedback, if vibro-tactile is appropriate for them, which is good, vibration. But if you keep vibrating all the time, and trying to, for example, a veering, when you have two different patterns of vibration, short, short, fast, and fast, fast, short. And again, just like the cuckoo and chirping sound, you add additional layer of interpretation on the information they receive. And if they forgot, okay, so what does this pattern mean? Does that mean I need to go left, or does it mean I need to go right? And adds additional confusion to them. But if it's for warning, so that, just simple one, vibro-tactile information will be helpful for them for dangerous warning. And they need the method. They want to repeat the warning system in case they did not catch what does it say. They can repeat it and allow automatic activation of walk signal, and maybe that too. Activating from a smartphone device, mobile device, that will be great. So they don't need to find a push button anymore. So here are some, based on those feedbacks, here are some of our design users interface criteria. So basically, we want to use the auditory or verbal feedback to users, tell them the information, vibration or tactile. The user's input, obviously the graphical user's interface is no use to them, and you don't want them to put the cell phone in front of their eye if they have low vision, and that kind of defeat the purpose of be aware of this environment when at the intersection crossing. So the input would be very simple, and this is what we're looking at. Initially, we only have single tap and double tap on the screen. So it doesn't matter what's the display on the smartphone. You just do a single tap and double tap. These are only two commands. And in the future, that may be able to use the speech to text, okay? But we are not implementing at this stage at this time. And Braille overlay, if the functionality gets more complicated, that we can put the overlay with like a 3x3 grid and with Braille tactile on top of the smartphone, so they can feel that and press different location of the smartphone screen to, for different functionality. But again, at this stage, that we are using a single tap and double taps to provide the input to the system. Okay, a quick overview of the overall system structure. So based on those feedback, that in the center of the graph shows that the visually impaired, they have a smartphone device, and the smartphone device, there's been lots of motion sensors on the smartphone, accelerometer, digital compass, GPS. Those information could be used to locate the position of the users and roughly orientation of the users, and through the Wi-Fi or cellular network, which is already there. And we'll have to include the digital map of that intersection so that you know the reference, know the person where he is. And the Bluetooth device will be used to, because of the GPS accuracy, they'll be used to complement the accuracy of the positioning solution to know that they are exactly at this, for example, southwest corner of this intersection. When the intersection is kind of narrow, you don't know if they are on this side of the street or the other side of the street, or in Urban Canyon, in downtown Minneapolis, for example, you don't even know if you're exactly on this block or the other block or the next block. And the key issues is here, how do you get the signal information from the signal controller, which is not available at this time, because these are showing the signal phase, the walk signs, but these are not available. And that's why we are partnered with MnDOT and to get the signal information so we can make this available to the users. In our earlier a prototype demonstration, basically instead of putting people on the street and exposed to danger, basically it's right outside here. Basically we map this whole area and kind of program this as kind of a pseudo intersection at the mall area here. At each corner that we'll be able to test different functionality and to guide people to the different location and different corners, and using the interface that we developed. And this is the data communication structure. So on the top here, basically it's the signal controller. And we get the signal information from the signal controller cabinet and through the device called the data acquisition device in the middle there. And that will broadcast the signal timing information, phasing, to a database that right now housing in our lab. We call it MAPS, the database server. And the users will be able to interact with that server to get the signal timing information when they are needed. And obviously in that database there's reference to intersections and phasing direction, so you can get appropriate phasing as users are pointing in different direction. And the key elements there is on the upper left here. You see the USB I/O. As I mentioned, that we want to have the users to automatically activate the what you call pedestrian request, the walk sign. That's basically it simulates the function of push button. So when they confirm they want to cross, they basically our database, our system will send a device signal to the controller cabinet. Basically, it's the same function as the push button. So they don't need to push the button anymore, and they don't need to find the push button anymore. And right now what we're dealing with is, as you see on the right here, there's a MnDOT firewall. We want to make sure that all the traffic controller network is secure and not hacked. So obviously, we have difficulty getting through the MnDOT firewall at this time. So for our field experiment, what we're going to do is, in the middle that we're going to establish the Wi-Fi or cellular network there, so we can get those information directly from the intersection without going through the back path of the MnDOT network and coming to us. But eventually, if we could pair it up with the TMC controllers, that we don't need every device at the intersection. We can have a one connection to the TMC that we can get all the intersections that we need through our database, that it's much scalable. Because you're looking at one intersection at a time. When you tap into the TMC, that you have all the intersection information. So when users at different intersections, that they'll be able to get those information for all the coverage within the region. So you don't need to install every single intersection with additional device and things like that. And obviously that the data acquisition still needs to be there, because of we need to get the data, and that's how the device gets the data and send it through the network. But I think this approach could be more scalable in a much wider deployment. So here are some simple explanation about the user's interface. So the first one is showing the single tap. So basically, as they are using the phone pointing to different direction, so they can do a single tap. When they do the single tap, you tell them you're heading north. It's a Washington Avenue 4-lane, for example. Or if you're heading west, they'll tell you what that direction and how wide the street is. And there are some discussion about if we should tell them how, physically, if it's 10 meters wide or 5 meters wide. But we prefer to use 4 lanes, because typically users, they have good ideas about either it's a 2-lane street or 4-lane street or 6-lane street. And that gives them a pretty good idea about this. And so they can basically do a survey when they're at the corner of the intersection, point to different direction, and do a survey and get information about that information, about the geometry of that intersection. And the next step is basically when they determine which direction to go, they'll be able to use the phone and point it to the direction to go and double tap. And basically when they double tap, it will send a signal to the signal controllers, request for pedestrian crossing, which is the push button functionality, and also gets the signal information. And it tells you if it's not walk sign, it tells you to wait for walk signal, or it's time to cross, it tells you it's time to walk, you have how many seconds to cross. Okay, so when they are ready to cross, and when the system tells the users how many seconds to cross, then it was starting to count down, and at the last 5 seconds of the end of the cross phase, that you again tells you that you got 5 seconds left. So you want to make sure that you finish your cross, and when you reach at the other end, that wants you to make sure to confirm, so that because sometimes when people double tap, what happens if they don't cross? And so that we will have a device to know, have a mechanism to know that they cross, and then so we can continue to move on and to guide them to the next intersection, things like that. So what I'm going to do here is I set up a kind of a pseudo intersection here. We have no access to this intersection. This intersection is a pretty new intersection by the University Hotel, and on the southwest is a CTS building there, and some construction going on there. So basically, right now I just bypass the GPS, and I'm just showing you the user interface part of it. And let's see if I got the cell phone signal here. Okay. So basically, this is south, and this is east direction. So basically, when they are at the corner and the intersection, right now I'm just going to assume the user's at the red dot, because I mean I'm not physically there. But when you point and do a single tap, okay, and
you are pointing to south, Beacon Street, 2 lane.
So basically, you're telling that when you're pointing south, it will tell you that what street is and how wide it is. And right now, if I'm pointing to east, I'll do a single tap.
You are pointing to east, Harvard Street, 2 lane.
Okay, so I kind of do a survey about the environment. So when they are ready to cross, they can do a double tap. And let's see, I think I have cellular signal here, so we'll see. So
Please wait while data is fetched.
So it tells you that it's processing your request. And every 5 seconds, it will tell you.
Please wait for walk signal.
So basically, it tells you, please wait for walk signal. And every 5 seconds, you don't need to keep double tapping. It tells you every 5 seconds, it updates you the status. And when it's time to cross, it will vibrate and inform you that it's time to cross, and also verbally announce.
Wait for walk signal.
Okay, it will, when it's time to cross, when it's ready to cross, tells you how many seconds left, and vibrates to alert you that it's time to cross, and tells you, I mean, how many seconds available.
Please wait for walk signal. Walk now, 22 seconds left.
But I don't know if you can hear it. It vibrates and tells you now 22 seconds left to cross. Okay, and then let's wait. I mean, another 17 seconds. It will tell you toward the end of the walk phase.
5 seconds left.
Okay, so you have 5 seconds left, basically telling that, well, you might want to hurry up, or tell them,
Time over.
okay, tell them this.
Double tap again to confirm.
Okay, so this is kind of the sequence that will tell them, well, the time is over now. Okay, and then you want double tap to confirm, and then when you reach to the other side or go to the next block again, that you can single tap, double tap again, and go through the same.
You are pointing to south, Beacon Street, 2 lane.
Okay, and what happened if you're pointing to the direction there's no crossing? Okay, so let's say try this. I mean, on the west, there's basically no crossing, right? So if I pointing to west and do a single tap,
You are pointing to west, 1 block to Union Street.
it tells you 1 block to Union Street. It does not tell you there's a crossing at all. So basically, in our digital map, that we maps this intersection and telling them what are the configuration with this corresponding to the next intersection, things like that. So what we're going to do next is we got the IRB approval, and what we're going to do toward the end of March, or hopefully that we'll be able to get everything all set up and that this is the intersection that we're going to take the group of visually impaired person going through this intersection. And this is at Golden Valley, Highway 55 in Rhode Island. And it's a 5-lane crossing across the Rhode Island. And we'll be taking them from the northeast corner to crossing to the northwest corner. The walk time is about 23 seconds. The total crossing time 23, walk 7 seconds, and don't walk 16 seconds. Right now there's no APS installed. And what we like to do is we want to bring people there because there's no APS. So we'd like to have them do basically 2 crossings. The first one is just using their regular existing skill. And we will just let them about 50 to 100 feet away from the northeast corner. So they will live there and using their existing skill as they are approaching the intersection. And we're going to observe how do they approach the intersection. And if they are free to use push button if they want for the first cross without any assistance at all, and to cross to the destination on the other side of the street. And the second task will be basically we're going to provide them with this smartphone device. Okay, and again, same origin, same destination, and we want to observe what kind of different behavior, what kind of different performance as they perform the 2 similar tasks with and without the assistance of our device. And here's are the measures that we like to look at. The subjective measure basically want to make sure that if they feel there's a sufficient time for them to cross at this intersection, and if they feel safe at this crossing, do they trust the system? How do they feel about this system? Do they trust, and do they think that the user's interface, that information is useful or satisfactory? And on the objective measures that we want to look at their walk speed compared at the sidewalk versus the crosswalk. Because if you started only at the beginning of the crosswalk, there may be differences because, what's their regular speed, and everybody might walk differently. So we can compare their walk speed at sidewalk and also the crosswalk, the initial alignment, the time to step into crosswalk. Is there a difference? If they don't receive any assistant information, the time to step into the intersection, does that differ from with the smartphone device? Veering and assistance that needed from the OMM specialist. And obviously there's, danger concerns. So our orientation and mobility specialist will be a shadow follow the participant about 3-5 meters behind in case there's an emergency that will be able to get them out of the danger. And so this is what we're going to do in the next couple months. So this type of decision support tool is what our goal is to provide decision support for the visually impaired, and this could be also for the elderly or disabled person. But the goal is not to replace their existing skill. When I present this to the visually impaired community, the person concerned about, well, yeah, this is great. And when people rely on this, they lose their existing skill, and that might be a concern. So we don't want this to be a tool that people, replace, that make them, forget their skill. They forget about how they can walk around themselves. And we want to complement this device with existing systems, and if not replace, and want to provide a more integrated solution for navigation and wayfinding. Obviously, intersection crossing is only one component of getting from A to B. There are other scenarios, situations that they face. For example, when they take transit, take buses, they need to get off, get transfer. Obviously, getting transfer often required a crossing at an intersection. But sometimes when they get off from the bus, they don't know where they are. Should they go toward the bus traveling direction or toward the back of the direction to get to their transfer connection, things like that. So there are challenges for this. As I mentioned that the GPS reception in urban canyon is an issue, and that's why we would like to complement, include the Bluetooth ID, to use that as a geo ID to help us better identify the exact location when the position is an issue. And the veering warning, at current stage, we are not addressing the veering warning problem in our research, but we'd like to look at that, and how we can provide veering warning at the crosswalk, and also accuracy and of the sensors on the smartphone. And I personally believe that with the smartphone technology, all the sensors on there gets more accurate, much better, and with higher performance. much wider available to everybody. And we also like to understand the cognitive demand. When people using this device, are they getting distracted, that they are not paying attention at the intersection? Or does this cause a problem that they will not able to process the additional device? We hope this device will provide sufficient information for them, but not overload their cognitive load. And we also like to evaluate, the acceptance. That is very important, satisfaction and trust. Because oftentimes, in the history, we can design a very accurate system, put on GPS and the camera on the goggle, backpacks, and all that stuff, but people don't want to use it. And I think this is one of the very important criteria in our design here is we want people to use it, and that they can use this device and they can be helpful, useful for them. And so this is one of the areas we want to focus on for our future work. And these applications, some may argue, well, this is good for visually impaired, but how about the other people with disability? And I see that's application for elderly or the disabled person using this device when they are in the unfamiliar environment. This could be useful for everybody as well. And veering warning, that is an area we like to work on. And as I say earlier, that orientation and direction at the bus stop, when they get off the bus, where do they go? Do they move forward or they should go backward to get to their connections, transfers? This could have the opportunity to integrate with the bus arrival information. For example, when they're arriving at the bus stop, that the smartphone device will be able to connect to a server or some sort of device getting the information of the arrival, the bus arrival information. Right now, currently, every Metro Transit buses, as they pull at the bus stop, if they see a visually impaired person with a white can, they are told to open the door and ask and tell them, this is bus route 6, for example, and I'm going St. Paul or going to the Bloomingdale or whatever that is. So they're required to do that. And for them, they don't know which bus that is. So with this, they'll be able to tell them now the arrival bus is whatever that is. And if the bus is not here, they'll be able to provide bus arrival information, which is already available at, in downtown Minneapolis as a part of the Mark II project that are showing those display. But these could be available to a visually impaired person as well through the smartphone. And wayfinding, indoor and outdoor, that this could be extended to the next phase, that by looking at wayfinding when they are, for example, in an indoor environment, Minneapolis Skyway system, getting them from A to B, and outdoor navigation and wayfinding. And ultimately, it will be also to include the route planning and guidance information. Couple final slides on how does this tie to intelligent mobility applications. As you see that our federal government is recently is very focused on the connected vehicle initiatives and how the vehicles can be connected. And there are areas that we're looking at connecting the vehicle to the infrastructure so we can do a better traffic management, knowing that the vehicle is coming and how many vehicles are there, things like that. And what I see is connection between the vehicle and the pedestrian and the infrastructure as well. And so two simple example is, for example, when a visually impaired person at the intersection crossing using our device, that will be able to broadcast those information to the vehicle drivers, knowing that there's a visually impaired person at the crosswalk or at a corner of intersection. They want to be more cautious about this situation. And on the other side, when this person, the visually impaired person at the intersection crosswalk or at the beginning, when they're standing there before they cross, that if there's a situation that through the V2V infrastructure, knowing that there's a potential red light runner, you want to tell the users not to cross instead of telling them to go. Maybe you want to hold that phase and tell them, well, you want to wait till the next phase and to let them avoid that kind of danger. So I see there's a connection there to communicate between the vehicle infrastructure and the pedestrian, and how these could be provide information among these three groups and to provide a much safer environment for both vehicles, infrastructure, and pedestrian. And certainly there are other applications, could be for bikers and in other modes as well. So with that, I conclude with my presentation, and I'm more than happy to answer any questions that you may have. Thank you.
Thank you, Chen-Fu. Are there questions?
Yes. I noticed that when you were doing the demonstration that you said, or it announced 22 seconds for the walk time, and then it was 17 seconds later it repeated 5 seconds for crossing time. It seemed like rather an odd number. Was that picked, or what's the algorithm for choosing how long you take until you repeat the next message?
Sure. Well, the first question, the first duration of walk phase is directly from the signal controller. So if this crosswalk has 23 seconds of crossing, whatever that number is, but we do subtract 1 second. Okay, we want to accommodate the data communication delay. So we purposely subtract 1 second, okay, in that case. But every 5 seconds to provide them an update. And that number, 5 seconds, you said it's kind of odd. We just pick it off the air because we want to provide users with feedback. Because when people are waiting for 5 seconds, it feels like waiting for minutes. So we provide an update knowing that, well, the system is responding to his request. So he's knowing that, we are doing it, telling him, updating the current status. We can change it to 3 seconds or 2 seconds. That may be more annoying, but that is, that could be changed to whatever. So as part of our field experience, maybe we'll get some feedback on that, and we can change to whatever time interval is more appropriate. Maybe instead of 5 seconds, change to 10 seconds. But I kind of like to be, 5 or maybe between 4 and 6, because typically it gets an update every once in a while, and then you know that the system is processing your request. It's not dead or, stalled or whatever. So I think that is helpful. It's kind of a feedback knowing that, well, we're still processing and just patiently waiting. So that number could be changed to answer your question.
Not exactly. The 5 seconds I understand, but in a demonstration, when he started to walk, it was 17 seconds later, and then it was when there was 5 seconds left.
Okay.
And it was, that 17 seemed like rather an unusual number. It wasn't, you have 10 seconds left, you have 5 seconds left, and don't trip on the curb.
Yep. Sorry, I apologize that I misunderstand your question. So when they are starting to cross, during the crosswalk, so you say that 17 seconds later, that tell them that it's 5 seconds left. So it's actually not the 17 seconds. It's whenever, doesn't matter how long is the crosswalk width. Toward the end of the phase, 5 seconds. Actually in the program, it's, we put it between 4 and 6. Whenever the controller sees that there's only about 4 or 6 seconds left, they'll announce and tell the users that you only have about 5 seconds left. You want to finish. Okay, so it doesn't matter how long is the crosswalk at the beginning. So if it's 10 seconds left, toward the end of the 5 seconds, that the system will announce you have 5 seconds left. And sometimes it'll tell you 4 seconds. Sometimes it'll tell you 6 seconds left, somewhere around there. And we just put a window there because we don't want exactly 5 seconds. Because this.
Do we have a question from our online audience?
How does the device keep someone from veering out of the crosswalk once they initiate their cross?
As I mentioned that, this device currently does not provide veering warning, okay? Because right now we do not want them to use their phone and scanning around when they are doing their crosswalk. When they are crossing the crosswalk, we want them to use their cane to continue listening what's the environment and to do the crosswalk. So when they are surveying at the corner of intersection, they get those information, and when they double tap, they confirm, they can put those in their pocket, so they can still hear it, but they can use their cane to cross. And at this stage, we are not providing veering warning, which will be the next stage that we would like to work on to provide the veering warning for this device, but it will probably not using the sensor from the phone. It will probably be through additional mechanism to provide the veering warning and to alert them through the smartphone device and provide them the feedback and tell them you are veering to the right or to the left, things like that. And there's additional challenges on that part as well. When people are veering, what kind of information is appropriate to help them to veer back. When they are veering about, 10 degrees, 15 degrees, and so there are areas about what is appropriate, and sometimes people's understanding, they might, over adjust. So now they are veering to the right, and they hear that message, they over veer to the left again. So that's the area we would like to work on next. But right now, this device does not provide the veering warning at this stage.
Sorry, I was a little bit late to come to this meeting. Maybe I missed something. My first question is how you calculate the speed of crossing based on different type of people who has different type of mobility problem. So how we calculate that distance and how we find the time. The second question is the configuration of the road. We have some road just 2 lines, and some of them have a median. And how we, in this environment, how the device recognize the configuration of the road to calculate the time, to calculate the working speed of the person who is using the device. And the last question, based on hearing loss of different people, how you calculate the hearing loss of the person to understand what the device is saying, and how to sample the population.
Sure. Thank you for that questions. Well, the first one is how do you determine the speed? Well, we don't determine the speed, but when the public agency, they design the walking phase, when traffic engineers that they design the walk phase, that they basically use this kind of average walking speed, I think it's around 3 miles per hour walking speed, and for their walk phase design. And that's how it determines, depends on how wide is the street, what is the average walking speed, and that use that number to determine how much time is needed for at the crosswalk. And oftentimes these are not sufficient for elderly, disabled persons. So one of this, our approach is for persons that are visually impaired, because that, we could have them register, we know them, they are visually impaired, they use this device. So what this system could do is, there's opportunity to extend that walk phase by calling, calling for a pedestrian phase that will be able to extend that. But that is not the thing we implemented right now, but I see that there's a potential to do that if people walk much slower. And second question regarding the mediums and different intersection geometries. So we survey the intersection, we have the digital map of it. So as they are pointing in different directions, we tell them that right now what we said is a 15 degrees cone angle. So basically if I'm pointing east, that's helping the intersection crossing kind of aligned to the direction. But what happens if they point it kind of 45 degrees, tells you the direction, but there's no crosswalk there. Okay, so for the medium, that in case that they're pointing to the west and there's a medium there, we tell them that this is 4 lane and there's a medium in the middle, things like that. So we can incorporate those information in our digital map by announcing whatever that intersection geometry is, and we can also tell them that this is not a standard rectangular intersection and things like that. And in DC area, you see a lot of kind of a pentagon shape or multiple approach intersection, and that is more challenging. But we think that, with this kind of setup and with the map, that we will be able to provide them the proper information and tell them that, this crossing is, for example, 35 degrees and whatever that is. It's not different from a standard regular intersection. And the last question, if I remember, is regarding, remind me again, I don't, say it again?
Hearing loss.
Oh, the hearing loss, that's right. Okay, obviously, personally, I will have the same problem when I'm at the busy intersection. You can hardly hear the smartphone speaks, the phone speak. So one approach is we use the Bluetooth earphone. You can put it on one side pair with the Bluetooth, so you can hear it clearly and you can adjust the volume. And I don't know, I haven't asked a person with hearing loss if they already has a device there and how will that work, but I have to look into that. But using a Bluetooth earphone could be one device, and so they can hear that clearly, and they don't need the hands to hold on to anything. And another approach is to use a Bluetooth kind of a speaker that you can click onto your collar. If the visually impaired, they don't want to completely plug their ears. and they can still hear it, and they can hear the speakers, nearby. So that's kind of the approach I would do. Yes.
Information. What kind of information has to be sort of in the system in order for this to work? I mean, traffic signal information and, maps and things like that. What do you need there, and what has to be specially programmed?
In addition to the signal timing information and the mapping informations, that we have an algorithm to determine that, when people point in different directions, and when they cross, after cross, how do they get from point A to point B, and what are the nearby, because we are not just looking at one intersections. In our algorithm, we're basically looking at the grid, one intersection ahead, one intersection behind, and one intersection to your left, and one intersection to your right. So there's basically there's a kind of a mapping and guidance algorithm, knowing that where is this person with corresponding to the nearby location, so we know what is the next street is, and to determine, if they want to go that way, what is out there, things like that. And oftentimes when you provide navigation and guidance to people, it'll be helpful to kind of give them a heads up on what is coming. For example, if I'm this intersection and telling them that, the Washington Street is the next block, or things like that. So they can kind of get a sense of direction they're heading and where they are, things like that. So I don't know if that answers your questions. But
Jen, I'm curious about how the University of Minnesota is implementing some of the results from your study. And second of all, I wanted to know why you chose Highway 55 to work on visually impaired individuals, and why you didn't just try to implement this work around the university.
Yes. Well, the intersections on the campus here, it's all controlled by the city of Minneapolis. Okay, and city of Minneapolis, because to get the signal timing information, what we required, right now we just leverage the research from Henry Liu using that smart signal, so we get the signal timing information directly. And the reason we choose 55 is because MINDA, they are implementing the smart signals along Highway 55 for a separate project on highway performance and things like that. So we just tap onto that and use that as a mechanism to get the information we need. So that's the primary purpose. But Sandy from the PTS here, that she's very interested in having the one intersections that we can set up for testing here on campus. And that is the intersection that I show you, that on Beacon and Harbor, that intersection, she's very interested. So, if I don't know who owns that intersection, the university or city of Minneapolis, but we're more than happy to set up one here and do those type of testing. And there's lots of students here, then we can use that. So the answer is convenience, because MINDA already doing that, so we kind of leverage whatever the effort there. So yes.
There's a concern for the visually impaired with the roundabouts that are going in and around, and I saw you had a drawing up there of one, or a picture of one. Could you explain how this would work there too?
As I interact with the visually impaired persons in this area, the runabout is posing some challenges to them. It's difficult, and oftentimes when they get off bus, I think it's 66 and Portland. The bus stop, I think, is kind of after the construction. The bus stop there, once they get off, it's difficult when you arrive at the new location. You need to first kind of find out where you are. Just like when we go to a new city, that when we get off from a bus or a train, where am I? Should I go this way to get to the exit, or that way, things like that? And same thing for them, and they don't know what is the environment. So they need to know, okay, where the location is. And that is very challenging to them, because for runabout, particularly at the corner of runabout, all these are curved. Okay, and they have hard time to find out, okay, what exactly is the crossings, where is the crossings and what direction to go. And so when they need to take a transfer there, that causing some issues over there. And I do not have a fully solution answer to that, because obviously we can provide some information, but the walk is kind of, it's curved. Basically the runabout is curved all the time. But I think our device can provide information. okay, as they point to different direction, that they'll be able to provide some general sense of orientation and where they are. And but I mean, I do not have a full answer on. I mean, if this will definitely at this stage it will not solve answer the questions we have right now. But we see this as some potential, and it will require some additional investigation how we could better provide the information when people are at the roundabout on different sides, and how to provide the proper information so they can get to the next destination.
Any other questions for Chen-Fu? I do have one more, and then hopefully this will be quick so we can wrap up. But I wondered about training for the field test that you're going to be conducting. Will the individuals be trained off-site? Sort of this is how to use the technology in a test intersection, and then kind of let them navigate through sort of unknown with that odd-shaped intersection that you'll be using for the test?
Sure. As I mentioned, that Linda Spaulding, she's a certified orientation and mobility specialist. She will be the person helping us doing the training. So basically, the training will focus on the user's interface. We'll tell them that these are the interface that the system will function. Single tap, double tap, and these are the responses that you will hear. Things like that. But we will not testing at the intersection because we don't want to kind of distort whatever the environment setting. But basically, we'll teach them how to use the system and what kind of expectation that they will hear, they will listen, they will get. But no, we are not going to test them or train them at the intersection, but we'll be off-site, tell them how this system works, and we'll go from there.
Well, please join me in thanking Chen-Fu for his presentation today.